Hi, everyone. Today we will discuss security considerations when working with AI-generated code and what we can do to make our applications more secure. Let me tell you what happened to me recently. I was building a contact for my personal website, and I asked an AI assistant to add an endpoint for submitting messages. I got back working code, and I tested it, and the form submitted perfectly. But there was something happening behind the walls there. I was about to deploy, but during the code review, I knew something. And there was a get end I didn't ask for. Anyone with an endpoint could retrieve all of my contact messages. I caught it immediately, but what if I hadn't? What if I just tested that the sub worked and deployed? This isn't a one-time thing. AI-assisted development makes us incredibly fast at building features, but in that speed, security often gets deferred. Because in prototype perspective, it can be handled later. Does the form sub? But we don't test the attack path. We don't test the endpoints we are created along the way. Security requires context that emerge during development, and ultimately, you are responsible for what you deploy. These are the questions that often get overlooked in fast development. Who might attack my application and why? What data should never be public? How will this behave in production? And what happens when things go wrong? Can logged in users access each other's data? These questions don't have obvious answers at the start because they emerge as you build. Today, we will explore how to recognize when these questions matter. This talk is for developers using AI assistants for coding, anyone deploying AI-generated code to production, and tech leads reviewing AI-assisted PRs. If you are building with AI and shipping to users, this is for you. Let's start with a fundamental rule. Never expose keys meant for backend in your frontend code. If it's in frontend code, it's public. Even if it's minified or obfuscated, it's public. Here's what often happens in fast development. Backend-only keys end up in front-end code. Database URLs or admin API keys get exposed. Keys are hard-coded instead of using environment variables. There is no distinction made between front and safe keys and backend only. It works, so it ships. What counts as exposed? If it's in your JavaScript bundle, even minified, it's exposed. In your mobile app binary or in local storage or session storage, it's exposed. In URL parameters, exposed. Attackers can see in practice. Quick, list your keys and secrets. Search your front-end code for them. If you find backend keys there, they need to move. Ask yourself, is this key visible to the browser? If yes, ask this. Having this key visible in the browser, is it really safe? If you are not sure about where is a key used, you can still ask your AI agent to trace it. Let's talk about third-party dependencies. Libraries get added to solve problems, but it isn't part of the default flow. Outdated versions with known exploits can slip through. Import methods don't warn you about security issues. Front-end dependencies are especially risky because third-party scripts have full access to your web page. They can read passwords from your user inputs. They can access cookies and session tokens. They can even capture keystrokes. You are trusting these scripts with your user's credentials. So it is crucial to manage them well. Here's the scenario. You need image processing and you install ImageLib version 2.1.0. It's popular, it works, so it's great. But version 2.1.0 has a known remote code execution vulnerability. Version 2.2.0 fixed it, but you didn't check it in the first place. Your server is now vulnerable. This happens because package gets installed without vulnerability scans. Older stable versions get used. Transitive dependencies may have issues you never see. CDN imports make security scanning, version locking, and persistency, but package managers would give you all these. It may provide you reliable audit methods and version locking. A pre-bundled image that won't change until you redeploy can prevent some potential issues, and as a developer, you wouldn't even know the risk you just dodge. Initial development focuses on the success case. User enters valid data, gets valid response, and everything works. But real users encounter failures, delays, network issues, and edge cases. We test the happy path, but users may experience the unhappy path. These are the states we often forget to handle. What does the user see while waiting? What happens when the API fails? What if the data comes back empty? Each of these missing leads to a poor experience. Duplicate submissions, exposed error details, or frozen interfaces. Why does this matter for security? Handled errors might expose internal details. They can expose stack traces, database names, file paths. Retry logic without idempotency causes duplicate transactions. You can imagine double charging a payment. Missing states cause duplicate form submissions. These aren't just UX issues, they are security gaps. Here is a systematic approach. For each page or component, ask, what are all the possible states? Loading, error, empty data, success, partial data. Then check, does each state have proper handling? Let me give you a concrete example. You have an image upload box, and what happens if the user tries to upload a video instead? Do you validate the file type? Do you show a clear error message? Or does it silently fail? Or worse, does it crash? Go through these one by one for each component. And what does the user see while loading? What happens if the API returns an error? What displays when there is no data? What if data is incomplete? This isn't just for beginners. Experienced developers do this already. Map the states, then verify each one is handled. Don't assume it works. Make it. Remember the contact forms from the beginning. Here is the pattern behind that happened. You ask for one endpoint, but you may get a full set of CRUD. You need to create a single resource like a post endpoint, but you may get some extras along with it. This is because agents are used to seeing these operations together and they go on autopilot, complete the pattern. REST conventions get applied automatically without security consideration. Look at the pattern here. You may ask for one operation. You might get more than you ask for. A post becomes full. A simple create endpoint comes with real state and delete. Each extra endpoint is a potential security issue you didn't plan for. And when it comes to endpoints, more is less. This is very important. Why does this happen? Training data is full of complete CRUD examples. Create, read, update, delete for almost every resource. REST conventions include all HTTP methods by default. pattern completion gets prioritized over minimal exposure. The code is being helpful by finishing the pattern, but security requires minimalism instead. Only expose what you actually need. Take time to understand what data your application handles. What information are you storing? What is sensitive? You need this for GDPR and privacy policies anyway, but it also fundamentally shapes your application design. When you understand your data, you can make better decisions. Should users delete messages or should they be permanent? Should profile change take effect immediately or require verification? What happens? What operations actually make sense for this data? This understanding prevents problems before they start. You won't build unnecessary endpoints if you understand what should and shouldn't be exposed. You won't add a delete button in the front end for data that should never be deleted. Know your data. Let that knowledge guide what you build. Let's talk about how can we audit this. First, list all your routes, and your framework might have a tool for this. Then question every single endpoint. Do you need to list all users? Can any authenticated user retrieve any other user's profile? Should users be able to edit each other's data? Should account deletion even be exposed as an endpoint in the first place? Or should that be an admin-only operation? Go through every endpoint and ask, did I actually need this? Should this data be accessible this way? There is a critical distinction here. Authentication answers, who are you? It verifies identity. Authorization answers, can you access this specific resource? It verifies permission. Being logged in doesn't mean you can access everything. Authentication is about identity. Authorization is about permission. Authorization requires understanding user groups. Who uses your application? Regular users, admins, maybe guests or moderators. What can each group access? Regular users see their own data. Admins see everything. Define these groups and their permissions. It shapes every authorization decision you make, and you are not just checking are they logged in. You are checking does their role allow this action. Here is what typically gets implemented. Authentication works correctly, users log in, sessions are managed, identity is verified, but permissions checks are frequently missing. The code verifies who you are, but not what you are doing. It checks if you are logged in, not whether your user type allows this action. Admin accessing admin data, fine. Regular users accessing another user's data, that should fail, but often doesn't. Here is a concrete example. User A is logged in and authentication passed. User A requests get user 123's profile. The system checks and the user is logged in. So check passed. System returns user 123's profile data, but user A is actually user 456. So they just access somebody else's private profile. Let me show you what it looks like. I'm viewing my order confirmation. The URL is /order/12345. That's my order number. And I change it to /order/12346. Just the next order. And I hit enter. Now I'm looking at someone else's order. Their shipping address, what they bought, when they ordered it. This is called IDOR, Insecure Direct Object Reference. The ID in the URL was not validated against the user making the request. Looking at this table, has the same problem. The authentication checks is there, but the ownership check is missing. We verify who you are, but not whether this resource belongs to you. In rapid agentic development, it's easy to miss these controls, especially when you leave the responsibility to the AI. One agent might leave it as a tomorrow's problem, but another might never notice it was missing in the first place. Why does this gets missed? Authentication is explicit. Every framework middleware tutorial covers it. Authorization requires understanding ownership and access rules, which emerge as you build. You don't always know up who should. These relationships become clear during development, not for. Here is a pattern. Top example, incomplete. It finds the order by ID from the URL. If the order exists, it returns it. No ownership check. But the bottom example, it's complete. It finds the order by ID and the user ID. It can only return orders that belong to the logged in user. The ownership question is this your resource? And we built this into every query that touches user data. Here is a common pattern in iterative development. You encounter an edge case, you add an if statement to handle it. Another edge case appears, another if statement. Over time, your code becomes a patchwork of conditions. Security checks scattered everywhere. Each patch solves one problem, but the architecture gets messy. Here's what patching looks like. We fetch the order, then patch one, check if it exists, then check ownership, then check if deleted, then check visibility. Each check was added as we discovered the need for it. This works, but it has problems. What's wrong with patching? Security checks get scattered across your code base. Every function that touches orders needs these same checks, and it is easy to forget when adding a new code. Did I remember all four checks? So inconsistent application is the development. One endpoint has all checks, another forgets one. This is really hard to audit. Where are all the security checks? You have to search the entire code base, and you have redundant code in your code base. Better approach would be prevention by design. Instead of checking for bad states everywhere, make bad states impossible. Enforce security at the data layer. If you can't fetch data you don't own, you can't accidentally expose it. The architecture prevents the problem, not individual checks. Here is prevention by design. The repository is constructed with a user ID. Every query automatically includes the base security constraints. Must match this user, not delete, and be visible. When you all find by ID, you can't forget the security checks. They are built into the architecture. You can't fetch data you don't own. Design prevents insecurity. Key principles of security by design starts with preventing bad states from being possible. Don't check for them, make them impossible. Validate at boundaries, trust internally, and check once at entry points. Trust inside your system. Fail closed, not open. When something goes wrong, deny access by default. The easiest path for developers should be the safe path. So make insecurity hard, security easier. When reviewing your architecture, ask, are security checks scattered or centralized? Could the developer forget a check when adding new code? Does the architecture make insecurity hard or easy? Is there a single place that enforces access rules? If developers can easily forget security checks, your architecture needs improvement. Design should guide developers towards secure code, not rely on them remembering every check. Rate limiting rarely gets added without explicit prompting. By default, every endpoint is unlimited. Any user can make as many requests as they want, and this creates problems. Without rate limits, every endpoint is open for use. Login becomes a brute force target. Registration gets flooded with spam accounts. Password reset turns into email bombing. The table shows the pattern. Each endpoint type has its own abuse scenario, and each one needs its own rate limit. Real impact example can give you a contact form as an example. If your contact form gets hit with 1000 spam messages per second, or your login endpoint automatic credential stuffing attacks, your API skyrocket from compute costs because someone's hovering your expensive endpoints. Rate limiting isn't just for security in this regard, it's cost control and availability protection. So, what to implement? Rate limits per endpoint type would be very useful in this case. Login gets 5 attempts per 15 minutes, conform gets 3 per hour. Rate limits per IP address can catch automated attacks. Rate limits per authenticated users can prevent abuse from compromised accounts. So you can ask yourself, does every point have appropriate rate limiting? The limits should match the endpoint purpose and risk here. Input validation often gets applied inconsistently. Some endpoints validate truly, others trust whatever input they receive, and validation logic gets scattered across the code base. One endpoint checks email format and another doesn't. This inconsistency creates vulnerabilities. Input field is an attack surface in our production applications. Email fields get script injection. Name fields get SQL injection. Number fields get impossible values. And without validation, all of this gets processed by your backend, which can be very problematic. Common validation inconsistencies can be exampled with validating on one endpoint, forgetting on another, or controller but not in the model, validating data type but not range, accepting numbers like negative numbers when it's not supposed to be there, validate presence but not content, like check the name exists but not what's in it. And these gaps create security holes. Better approach would be schema validation. Define validation rules once at the model level and enforce them everywhere automatically. Email must be valid email format. Name is required, maximum 100 characters. And age must be integer between 0 and 150. Use validation libraries like Joey, Yup, or Zot and define the schema once. So you can apply it constantly. You can't forget validation with this method because it's part of the data model. Development prioritize helpful error messages. Detailed errors aid debugging, and you want to see exactly what went wrong and where. But these same details help attackers understand your system. What's helpful for debugging becomes helpful for reconnaissance. Verbose errors are reconnaissance gold. Stack traces reveal your file structure. Database errors expose table and column names. Each error type leaks information attackers can use to map your system. Here is a real comparison. The example is the raw database error with the stack trace goes to the client. What does an attacker learn? You use Mongo database and the database name is my app. Collection is users and unique index on email. Also server file paths. And this is reconnaissance gold. Good example would be clean error object. Like in the example slide, error code lets your front end handle it appropriately, maybe show a specific warning, offer to recover the account or redirect to login. And the code gives your front end logic without exposing your backend internals. What to verify? Are stack traces disabled in production? Do database errors reach the client? Are error messages user-friendly or developer-friendly? And test with invalid inputs and check what responses look like. Log detailed errors server-side for debugging. Return sanitized errors to clients. And keep the details for yourself. Hide them from users. Debugging requires visibility into what's happening. Comprehensive logging helps troubleshooting. Log requests, log responses, log everything. It is very helpful. But logs can become a security liability. What you log for debugging might contain sensitive data. When you log the request body, you might passwords and credit card numbers. When you log user object, you might include password hashes or personal data. And all of this ends up in plain text and often sent to third-party services, which can be read by developers working on the project. And this is actually one of the ways how leaks happen in the real world. So why is this a problem? Logs usually stored in plain text. More people have access to logs than have database access. Developers, ops support. Logs got backed up, retained for months, aggregated across services. Logs often get to third-party services platforms. Your sensitive data is now in all over the place, accessible to more people longer than the actual data sometimes. Better approach would be being more intentional about what you log. Don't log entire requests or response objects. Log specific fields you need for console log request body, log the action, user login attempt for email, and instead of logging the entire user object, log user 1, 2, 3 updated profile fields, name, avatar, etc. Structure your deliberately. What do you actually need to debug this? Log that specific information, not the whole object. Let's talk about hardcode secrets. Testing something, you hardcode a secret to make it work quickly, and it works. You commit the code, and now that secret is in your Git history forever. Even if you remove it later, it's still there in the repository history. Anyone with access to the repo can find it. Database credentials, AI keys, JWT secrets, admin passwords, they all end up in the code as plain text constants. Here are some usual suspects. Each of these should be in environment variables, not in your code. Why does this happen? Fast feedback loop. Hard coding the value lets you test immediately. Environment friction, and you need to set them up. Restart server, configure deployment. So during development, it's tempting to hard code first, move to environment variables later. But later often becomes never, and the hard coded secret gets committed. The fix is using environment from the start. Never hard code secrets, even for tests. Set up environments variables in your development environment. Frameworks support .env files that aren't committed to Git. Know your secrets and list them all. Make sure they are not exposed in your code. You can use search tools provided by your code editor to find them. Default configurations are designed to make development easy. They optimize for getting started quickly, not for production security. Debug mode on by default, and course allows everything. Default credentials are simple, and this works great for local development, but really dangerous in production. These defaults exist to help for getting started quicker and easier, and debug mode makes troubleshooting easier, and open core removes friction during development. But what helps you locally becomes a vulnerability in production. On the right side, you can see what production actually needs. Why do documentation optimize for getting started quickly? Copy paste from tutorial is the development convenience doesn't equal production security. The code that works in development goes to production without configuration review. It's easy to forget that works and secure are different requirements. So, what to check before this is course configured for specific origins, not wildcard? Are all default passwords and secrets changed to strong unique values? And are secure flags set, like HTTPS enforced secure cookie flags enabled? And you can review your configuration files, searching for debug, development, default, production configuration explicit without relying on defaults. Let's talk about common database security gaps. This happens in the fast development when the focus is making queries work, not making them secure. Four main areas are injection vulnerabilities, overfetching data, missing indexes, and no query timeouts. First, I will start with injection vulnerabilities. Top example includes a string concatenation builds the query, and user input goes directly into SQL. And with this method, an attacker can inject malicious SQL very easily. But in the bottom example, with the parameterized queries, the user input is treated as data, not as code. Use parameterized queries or ORMs that handle this automatically. Never build queries with string concatenation. Second is overfetching data. Top examples shows fetching the user and returning the entire object. And that object may include password hashes, internal IDs, and everything else. And when we take a look at the bottom example, we can see that in that example, we only select the fields that we need. So only returns the values client is supposed to see, and this prevents accidental exposure and improves performance. Two more considerations I can mention, and I can start with index your authentication fields, email, username, whatever login, because without indexes, every login does a full table scan, which is very slow and resource intensive. As your user base grows, this becomes a security risk because someone exhausts your database with login attempts. So you should set query timeouts, and that long-running queries can exhaust base connections without that. And timeouts prevent single bad query from taking down your system. Let's talk about architecture. Security with understanding boundaries. Where does trusted mean in your system? Trust boundary emerged through design. Front-end trusted? No, user controls it. Is your API layer trusted? Only after authentication. Is your database trusted? Only if your application layer enforces rules. Understanding these boundaries shapes your security architecture. In depth means multiple security layers. Each layer provides protection. CDN and WAF block malicious traffic. Load balancer applies rate limiting. API gateway handles authentication. Application layer enforces authorization. Database has row level up security. If one layer fails, others still protect you. Don't rely on a single security layer. Fast development produces simple architecture. Internet to application database. All security in one place. If that layer fails, everything is exposed. Layer architecture distributes security across multiple points. More complex to build initially, but more resilient. You don't need all these layers from day one, but understand where you can add them as you grow. I'm going to talk about principle of least privilege here. And you should grant only the minimum access needed. Your database user shouldn't have admin rights. Just read and write permissions for specific tables. And your application shouldn't root, should never have wide scopes. Should have minimal scopes. If you only need data, don't request permissions. Also should have permissions. So don't make everyone an admin. When something gets compromised, this privilege limits the damage. We are closing to the end. So we covered a lot of security patterns, and let's talk about mindset. Treat AI assisted code like code from a brilliant colleague who doesn't know your project's context. It's fast, productive, gets things working, but it needs review before merge. This colleague is excellent at solving problems, but doesn't know your security requirements, your data model, or your production environment. Same principle applies to all code review. It works, you check edge cases. They say it's done, you check if it fit your project context. Whether it's AI generated from colleague or your own code from this week. Same review standards always be applied. Should be. One AI session starts fresh. Remember your previous feedback. Learn from past reviews. This makes consistent review habits even more important. You must catch issues every time. There is no learning curve. Build the checklist into your process, not your memory. Essential questions for every review are like what endpoints were added. You can list them, verify each one if they are really required to be there. What data is accessible? Can users access each other's data? What is the authorization model? Identity and permission checks. What happens with bad input? What gets logged? Any sensitive data exposed? What is hard coded? Any secrets in your code? Make this your standard review checklist. Before you deploy, run through this checklist. These are the questions we covered today: endpoints, authorization, secrets, error handling, logging, input validation, rate limits, and configuration defaults. Make this your standard deployment review. The mindset shift you need to make is, instead of asking, does it work? Ask, does it fail safely? Instead of, can I use it? Ask, can someone abuse it? Instead of, is it fast? Ask, is it secure? This doesn't mean sacrificing speed. It means thinking about security while you move fast. Security reviews becomes part of your development flow, not something you add at the end. One line to remember would be, test like an attacker, not like a user. Users follow the happy path. Attackers test edge cases, malicious inputs, and what happens when things go wrong. If you only test the happy path, you will miss the security issues. Think adversarially. What could go wrong? What would an attacker try? Make the part of your testing mindset. One line to remember is, test like an attacker, not like a user. User follow the happy path, attackers test the edge cases, malicious inputs, and what happens when things go wrong. If you only test the happy path, you will miss the security issues. Think adversarially, what could go wrong? What would an attacker try? Make that part of your testing mindset. So, what can we do next? We review AI assisted code with the same discipline you would use for any pull request. Add security checks to your development workflow. Test the unhappy paths, errors, edge cases, malicious inputs. Don't just test if it works. Test if it fails safely. The final thought for this presentation is that you ship it and you own it. AI help you to write it, but your name is on the commit. You are responsible for the security of your users' data. Make security part of your development practice, not an afterthought. Thank you. I think I closed it a little bit sharp. Uh, my presentation is done right now. Okay. So,
Okay, applause from Ahlen. Yes, I can share with you attending. So, is it visible or not? No.
I was
No.
targeting 30 minutes, but I had some sections that I thought I can also include that they can be useful. So it got a little bit
From
longer.
Ahlen.
Hello.
Okay, and back to other attendees. So, guys, if anyone have questions, feel free to type questions on chat, unmute your microphone, and just ask your questions. But from my side, congratulations, you did it. Amazing talk, amazing presentation. So let's start.